You are listening to EE Times On Air, and this is EE Times Current. I'm Taylor Marvin. Welcome back to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, Dr. Sonny Baines talks to four key figures at Innatera, a spin-out from the University of Delft in the Netherlands. They're hoping that their latest spiking neural network chip will become the AI of choice for people working on sensor applications. Discussion follows with Giulia D'Angelo from the Czech Technical University in Prague and Professor Ralph Etienne-Cummings of Johns Hopkins University.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sonny Baines.
For today's episode, Sonny is talking to four key figures at Innatera, a neuromorphic processing company based in the Netherlands. After the interview, we will be talking to Ralph Etienne-Cummings from Johns Hopkins University about the issues raised.
Thanks, Giulia. Innatera is a spin-out from the University of Delft, where the founders had been working for close to a decade on building energy-efficient processors and emulators to help neuroscientists with their experiments. I wanted to know more about Innatera, its technology, and what they're hoping to be able to do with it. I started by asking Sumit Kumar, a founder and CEO of the company, about Innatera's origins. He said they realized in 2018 that sensors were becoming complex, generating a lot of data, and therefore needed some kind of low-power AI to process their outputs.
Back then, there was very little understanding or acceptance in the industry that energy efficiency was going to be so critical for sensors. People thought that the next Jetson GPU that was coming out from NVIDIA was going to be power efficient enough that you could put it into every device, for instance, your smartwatch and your smartphone. But I think somewhere around 2020 was the first time that this realization came about in a lot of customers that power was going to be a very critical problem. And the only way to address that would be through emerging computing architectures, such as neuromorphic computing. And that's when, around 2020, we actually got funded. We raised our first round of investment, and we started building our chips and essentially sharpening our focus towards building better processors which are suited for sensing applications that we saw at that time coming out. Today, what we've done is really packaged up our neuromorphic processor in the form of a microcontroller, a companion for sensors. It's essentially the first chip that a sensor talks to when it produces data, and it allows you to extract meaningful insights from that data with very little power and very quickly. What we've been able to do in the last few years is really sharpen that and figure out where does the industry really require these solutions today? What is the industry ready for today? And where we see the meat of the problems really is in the area of pattern recognition. So essentially being able to identify relevant patterns inside large volumes of sensor data, which are coming out of these always-on applications. And I think for that, these event-driven capabilities of neuromorphic processors are really well suited.
So, as you've said, the area you're going for is sensor-based, edge intelligence, very often low power in the low milli or microwatt region with low latency, always-on operation. This is a large and diverse market. Can you talk about the various applications and sensors you have in mind? You mentioned event cameras, but can you talk about other kinds of things you're looking at?
Certainly. Where we think that neuromorphic does really well is in applications where power is a problem and latency is the problem. And today we see customers and generally the industry going in a direction where they're integrating sensors increasingly into battery-powered devices. So think of small devices like your smartwatch or a smart ring, looking at your heartbeat throughout the day, or think of your security camera monitoring the outside of your house continuously. And in all of these applications, you have this continuous stream of data, which a processor needs to look at as the data is coming in throughout the day. And because the device is running on a battery, the processor has to be very efficient. If it's inefficient in any way, it's going to show up in the lifetime of the battery, and you're going to have to recharge that device very often. Another problem is increasingly the sensors going into applications which involve some sort of human-machine interaction. And there, the latency of recognition is incredibly important, because if that system takes a few hundred milliseconds longer, you perceive that immediately. And it reduces the confidence that the user has. These are precisely the applications that we are targeting today. So we have applications that range from pattern recognition in radar sensors, which are being targeted towards smart security cameras and video doorbells. We have audio solutions where traditionally much of the data which is being captured from the microphone is simply thrown away because it's irrelevant. And the need for on-device AI is really high in these applications because privacy is a concern. You don't want to take data coming out of these sensors and stream it somewhere to be processed. It takes too long, costs too much energy, and effectively violates your privacy. So it's with these sort of fundamentals that we've developed our products. And today, the way we've designed the chips is by integrating a range of standard interfaces that allow the chips to be connected to a diverse range of sensors, everything from microphones, radar sensors, inertial measurement units, but also potentially to low-resolution image sensors and many others which are now popping up in the market. You can connect all of these with our chips and use the chips basically in exactly the same way.
To allow for the chip to be flexible enough for the diverse markets Sumit Kumar just described, Innatera had to build a chip with lots of types of functionality. As well as its own RISC-V CPU, it has various different flavors of input port, conditioning for various kinds of signals, and even both analog and digital neurons. I asked neuromorphic architect Petruk Bogdan, who goes by Peter, about the difficulties of trying to guess what his customers might need.
We know what we want the chip to do. We want it to be a single point of contact for sensors. This is the first and only chip that the sensors would need to be able to interact with to get actionable, intelligent insight on the edge. In order to do this, we can already, from this central requirement, we can break down what this means for the product itself. We can already predict that we need some sort of CPU to be able to handle all of these diverse set of sensors. Therefore, we already can predict what kind of interfaces we need to support by doing a quick market analysis of what kind of interfaces sensors require. And we know that the RISC core has to be there and how it needs to interact with the rest of the subsystems to be able to ferry data around, for example, for different kinds of applications. The flexibility that we've built in is also very much by design. We've designed our SMPT1 so that it's not over-optimized for a specific application. But we do know, for example, target power numbers for various applications from our customer interactions and our own application developments. So it's not necessarily a matter of second guessing. It's a matter of making some reasonable, intelligent, expert-based assumptions of how you would need to build the system and how you would need to spec the system, and then validating those assumptions through customer interactions, conversations, and internal developments.
Of course, there's always a trade-off between size, power, and specialization. I asked Vasily Toma, Vice President of Engineering, whether there had been a temptation to make the chip smaller but more specialized.
Well, the temptation is there every day, both for making it smaller or larger. If you look at edge AI computing, this market has been evolving in various ways during the last few years. So what you want to do there is to have a large enough nest that you can accommodate a variety of use cases, not just a few. So our first morphic microcontroller that we're putting out there, it is primarily to accommodate a larger amount of applications. And of course, compute fabric matters, but also what is important there, it is the flexibility, programmability, and interfacing to the sensors. So what we have done, we have created this modular architecture that down the line, and yes, indeed, this is in our roadmap, we can squeeze the maximum of performance and efficiency either by making it smaller, removing some of the computer fabrics, or make it larger, or changing some of the interfaces with more neurons. In our profiling so far of all the applications, the recipe that we have put it out there right now, it's at the intersection of both compute fabric and interface and programmability.
So your production chip is coming out soon. You haven't been able to put it in the hands of customers, but you've got a previous version that's quite similar. Is that right?
Exactly. We call this our evaluation platform, and it is very similar to our production version. So we have used that chip to gauge the user experience, both internally and externally. One major focus that we have for our technology is it to be simple to use and integrate. And being a startup, you start with an effort to validate all of your ideas first. So that means hack it through a lot of your components, and you make a lot of sacrifices just to validate as fast as possible your assumptions. But now we are at the stage where we have validated the majority of our assumption, and now we are focusing in improving the customer experience. And the ease of adoption, it is our number one priority right now. It didn't come easy. We try to validate our ideas, and we do that through calling out our industry partners or academic partners to test our technology and get that feedback. Some of that feedback sometimes is harsh, but that's good. This is how we are zeroing on the success of our technology. So what does it mean? We are now having a software stack that accompanies our silicon, which ideally would allow a machine learning engineer to craft an application using our PyTorch extension. And we are offering there a few tools. One of them, it is a pipeline API, which elevates the pain of a user of a lot of boilerplate code and is a unified way to create multiple applications for different sensors. Moving forward, we have an AutoML solution that should elevate, again, the need of being a PhD in neuromorphics in order to use our solutions. But at the same time, it will bridge the gap between an ML engineer, an embedded engineer, and a hardware engineer. So we are putting a lot of effort right now to do the heavy lifting and create, hopefully, a simple experience for our customers through our software stack.
Having both analog and digital neurons is an unusual feature. I asked Peter Bogdan why they made that choice.
Having both analog and digital neurons gives us a lot of flexibility, and then also allows us to provide that flexibility on to our customers. In certain cases, it's more advantageous to have, say, different topologies of networks executed, whether on analog or digital, that makes best use of the compute fabric there. For example, you could go for wider topologies, wider layers in the analog accelerators, but maybe you want to go very deep in terms of layers with your digital SNN accelerator. So it allows us to combine best of both worlds, or to tailor the application on the fabric that is best for it.
You mentioned fusion as one of the applications you're aiming at. My understanding is that you have 384 neurons on your current chip. And my guess is that you might have to use, one chip per sensor and then another to perform fusion. Is that what you have in mind? And if not, can you talk about how many neurons you actually need in order to do some kind of serious fusion task?
In the neuromorphic sense, there is a lot of talk about neurons and synapses and their number. But realistically, for the kind of applications that we're going for and the flows that we're following, a processing pipeline doesn't just comprise the SNN. It comprises some preprocessing, potentially encoding, yes, the inference that could be in an SNN, and some decoding. The number of neurons isn't necessarily representative of the amount of processing or feature extraction that you can do, because a lot of it can also happen in the encoding. So in terms of a solution for sensor fusion, we're aiming for a single chip solution, a single chip that can do all of the tasks, either inference or some sort of signal processing or feature extraction task on a single data modality or multi-sensor modalities. Of course, if the complexity of the application increases significantly, then because we've set up the architecture to be modular, we can scale it up or down depending on the needs of the application. And importantly, in all of this, we've also looked at the network sizes that are required for us to solve some of the tasks that we've talked about so far. And at the moment, we can do very reasonable jobs with order 100 neurons for the kind of applications that we were discussing earlier. So yes, the neurons could be perceived as few, but it's important to also recognize that the way that they're interconnected, the function of the synapses, the function performed by the hardware encoding blocks that we have also should feature into the count, and it's not enough to just mention neurons in this equation.
I understand. But what you were saying was, should you be in that position where you feel like a customer comes with a problem that's sufficiently larger than your chip was intended to cope with, then you could easily upscale what you're doing so that it's got a larger number of neurons and more input ports, to do some bigger set of tasks.
So we can engage with customers in a few ways. We have the flow that is maybe slightly longer interaction. Yes, we could adjust our SoC, our system on chip, to perform the customer's function. However, because T1 at the moment is very much a platform and is quite flexible, we also have other components on the chip that can take up some of the slack if really required. The SNNs are very capable for their size. We also can augment that functionality, their ability with CNN or with the RISC-V processor on the chip. So again, it's not sufficient to just talk about the capacity of the neurons in the network. There's always more to this equation and more that we can scale up to in terms of task complexity in this sense.
Vasily Toma agrees with Peter, but approaches the question in a slightly different way.
In any system, you have two options. One, you hit a brick wall. So basically, if you cannot fit your network there, then that's it. But also there is the other option where you can still achieve your functionality, but you have to pay in performance. And this is where we are right now. They're always going to be hit a wall at some point. But even if the application itself exceeds the number of neurons and synapses, we still do have a lot of reusable components in time so that you can still do and validate your network, but at a lower efficiency rate, let's say.
So it's about the fact that it degrades gracefully.
It decays gracefully, indeed.
Of course, neuromorphic systems are only partly characterized by their neurons. Just as important is the interconnection network which stores their intelligence. In a schematic they shared with me, it looked like Innatera were doing standard crossbars with analog components to do in-memory computation. I asked Peter Bogdan about the Innatera communication fabric.
You can definitely call it in-memory compute, as the multiplication is performed in the synapse itself, and the memory, the weights, is co-localized with this compute. So that's definitely the correct way of viewing it. So you got it right.
Amir Zeo is a co-founder of Innatera and acts as chief scientific officer for the company. I asked him whether they might be looking at using emerging technologies such as memristors in the long term, perhaps for those crossbars.
From the beginning, we made the conscious decision to use pure CMOS-based mixed-signal design paradigm, specifically using the digital assisted design on one end for the low-energy signal processing, and on the other hand for the high reliability of the data retention. Similarly, we use the analog-assisted digital design concepts for high granularity power management and control. Having seen the sixth generation of the silicon showing the excellent results, I think our initial assumptions were adequately validated. Indeed, we still believe that that's the right way to perceive our design goals. Having said that, I think NBMs certainly showing the promising results. So from our perspective, actually, we did two things. On our architecture level, we have made the appropriate provisions to accommodate the NVM-based accelerators within our system on chip. So if need arise, we can easily integrate it. Secondly, we are, together with our research partners, actively working to evaluate the maturity of the NVM technology and provide novel computation models and principles.
An important but difficult problem in neuromorphic engineering, especially for those who are trying to commercialize it, has been the software that customers have to use to make their applications work. I asked Peter Bogdan about his perspective on this.
So in the past, I did my PhD and postdoc on Spinnaker, and Spinnaker 1, at least the system, was very much meant to accommodate for both of the goals of the neuromorphic community. One of the goals is obviously to understand the brain and the functions and the behavior and try to extract that functionality and behavior, model it to try and get to larger scale networks that can explain some sort of emergent behavior, to then go and validate it against measurements in a wet lab or fMRI or whatever other measurements there are, and then keep this feedback loop alive and do large scale brain simulations. in that kind of a landscape where maybe neuromorphics is a bit more fractured in this sense, a bit like Spinnaker, where you have the goal for understanding how the brain functions and almost at the same time, or maybe for different people, how to compute like the brain in order to make, for example, sensor processing more efficient, then these goals tend to sort of diverge a bit. You don't have the same learning rules, you don't have the same needs and requirements for understanding the brain versus trying to make a product that is resilient, capable, and low power. What we are trying to do is simplify the process. You shouldn't need a PhD, at least not a PhD in neuromorphics, to be able to process data using our chip or to use our chip efficiently. What we're trying to do is make everything as few clicks, as few parameters, as automated as possible. And that for us meant making the choice for a PyTorch-based framework that can do, in the first step at least, the gradient-based optimization, something that AI or ML, embedded engineer or not embedded engineer, with no background in neuromorphics should be able to easily pick up and start using. So we don't need the same abstraction level as some of the other neuromorphic software out there. We need something that can easily bring a user up to speed and very quickly be able to deploy to the hardware to get a sense of the KPIs, make sure that the application works, and just start deploying it in real-world scenarios, solve problems.
So what about the future? A few hundred neurons now will provide a certain kind of functionality, but how many orders of magnitude more will we need to open up really new kinds of applications beyond those we've talked about so far? Amir Zeo is cautious about looking too far ahead.
Currently, with our targets, such as high energy efficiency, low latency, capacitive integration density, programmability, and ease of use, we, as of now, targeting immediate needs of our customers. Predicting the future is very complex. So let me try to answer from 4 different perspectives: application, system, sensor, and SNN, or biological perspective. From application perspective, currently within the neuromorphic community, we have a wide spectrum of applications, and not only in the consumer space, but in a large variety, like in biomedical space, manufacturing, agriculture, communication systems, drones, robots, and general attempts to replace the manual tasks. Going into the future, it might not be that there isn't a single application that will be decisive, but that this wide application trend just continues. Having said that, within dynamic systems, which require low latency, fast response on task demands, where not only individual tasks, pattern recognition is important, but also collaborative behavior might leverage biggest gains when using neuromorphic. From the system perspective, here the question is how to optimally regulate information flow, especially from the dynamic systems. Here, being able to process information in a single domain is a necessity. For example, avoiding multiple conversions from analog to digital signal representation, but being able to process entirely in a continuous time domain. And then a similar question, like being able to process information in a single domain, whether it's in a time or frequency or phase. And that's going through the complete signal processing pipeline. The third one, the sensor perspective. Here, we need to accommodate high data rates, greater resolution, low latency, and more accurate data, which leads to sensor readings control and error reduction. And these are most profoundly expressed in a high reliability and mission-critical applications. So for that end, we need to enable sensor regulation and hence being able actually to efficiently respond to the specific events, and hopefully in the future being able to anticipate these events. And lastly, from biological or SNN perspective, previously we mentioned some of these complexity aspects, but from the simple paradigm of the tiny brain, we think that not only the absolute number of these computational elements is important, but also what kind of computation capabilities or complexity they have. For example, in facilitating wide range of temporal behaviors, synaptic gain bandwidth control, and eventually being able to efficiently learn on edge. And final question, when? Here in neuromorphic space, it's an incredibly exciting area. And then we have seen exponential rise in scientific works and publications. And there is no really reason why this trend should not continue. So we expect that these new applications will come sooner than later.
Peter Bogdan also sees a huge potential for neuromorphic engineering and suggests that the neurons themselves are only a small part of what will make their approach successful.
I think the future for neuromorphics is very exciting at the moment. We're in a time when there's an attempted concerted efforts from academia and industry to standardize more how we do benchmarking and datasets, and generally a better understanding in the neuromorphic field of what an application would look like involving neuromorphics and what kind of developments are required, what kind of blocks are required to create products out of neuromorphic technology. So I think what I'm looking forward to most in the future is for neuromorphics to not be perceived as exotic, not requiring a PhD for it. And I think we're making great strides towards that. It's difficult for me to predict how long until people stop thinking of neuromorphics as something exotic. And generally speaking, the approach that we've taken for creating a system on chip where there are specialized components on the board, I think this resonated with me quite a bit from the time that I was at Spinnaker, and where you could put whatever different workloads on different chips, or that you wanted to be able to create the vision of the not conscious AI, but the AI that is capable of performing a real world task. I think you need this kind of diversity. And generally in the neuromorphic space, people talk of diversity of other things that are related mostly to the SNN itself and not to the rest of the brain. I like to think of the chips that we're building as insects, not necessarily in the sense of the capacity of the SNNs themselves. I remember seeing a talk from someone, so I'm stealing this idea, that a significant proportion, at least, of neurons that exist in living beings that are there because you need a redundancy, you need to survive in case some of them get lost, you need to adapt to novel environments, but also a lot of them are there because as a being you need to survive and you need some control over your internal state to be able to regulate yourself. And that's what a lot of neurons help with. If you strip away those and you say, we know how to make a chip survive, we know how to supply power, we know how to do power control and all of the other digital or analog mixed signals techniques that we use, what we're left with is the useful bit of the neurons that have more of a higher ability to be able to do some pattern recognition or feature extraction or stuff like that. So in the future, just talking about the number of neurons is maybe not the most useful thing, but that we can focus on the number of useful neurons and how they don't just help the being, our silicon insect, to survive, but be able to do something more that's more interesting, like what insects do in all of their various displays of behavior. And it's difficult for me to put any timeline, but this is the vision.
Sumit Kumar sees the applications and users as the primary driver for progress in the field, although he also recognizes all the research that's being done in academia.
I'm very excited, just as everyone else on the team is, about the future of neuromorphic, because I think we all see that we're only touching the extreme tip of the iceberg when it comes to applications. We're doing pattern recognition, finding patterns in sensor data, and there's so much more that we can do. Especially talking with Amir, you get a very quick sense of when you're looking at a biological system, in how biological beings really perceive their environment. Everything from ingesting data from the sensor, carrying out processing, doing complex reasoning based on that data, all of that's happening on these spiking neurons. And we see it as a very powerful paradigm to be able to bring this to sensors. The best way to describe it is, think of a world before microprocessors existed. What did that look like? And when the first 8086 came by, that kind of changed the world. It brought in very new capabilities. And I think we're at an age and a time where neuromorphic computing is doing just that.
Vasily Toma agrees and sees integration as being one of the keys to pushing the technology forward.
I just want to echo a little bit more what Sumit said, that our current technology, to see it now, it is indeed the tip of the iceberg. And it's not only just on the neuromorphic front, and I want to emphasize what we build around the neuromorphic components in making a great system. And that system, it is still a one chip. So our goal is to be the first chip that the sensor talks to, but going forward, we would like to be the single chip in the system. So increasing our integration density.
We end as we began, with Sumit Kumar, who points out the key challenge for both Innatera and the field as a whole.
The kind of take-home message for us as neuromorphs is to really think about how we can make neuromorphic computing more accessible, more usable by end users. A majority of the industry does not always care about what's inside the box. They want to have a problem solved. And I think that we have to have that sort of problem-solving mindset while we're leveraging the capabilities of neuromorphic computing. And I think as long as we're able to do that, we're going to be very successful at taking this technology into the market.
Thanks, Sunny. Let me tell you right away how much I loved the startup vibes they had and the energy they brought to the table. It was a pleasure to listen to this episode. And for more about Innatera's work, please go to brainsandmachines.net. Now, we welcome back our regular commentator, Professor Ralph Etienne-Cummings from Johns Hopkins University.
Hi, guys. Hi, Sunny. Hi, Giulia. Happy to be back.
So I would like to start immediately with the very first question. I didn't know much about Innatera, but I would like to understand a little bit better their chip. So I know that they do not work in subthreshold, and I wonder the difference in terms of robustness, reliability, and most importantly, the power cost they pay for that.
From what I heard, they didn't provide an actual metric of the power cost, right? They didn't speak in terms of details of what specifically that chip does, but the components of that chip seems to be pretty defined, right? So there's some elements of standard computation, like the RISC processor and so on, and then there's some elements of classical neuromorphics, if you will, with the spiking neurons and both digital and analog. And of course, then the combination of those items, the focus being on event-based, low power, edge computing, low latency. These are all the classic things that we want, right? So the tools that they are developing are going to be important and going to make some inroads in the community. So I am eager to see when the chip comes out, how folks can get their hands on it and actually play with it and see what it does.
So I just want to chime in here and say that we're used to dealing with academics. It's a very different thing when you're dealing with startups. I have to say that Innatera were very generous in that they gave me access to some documents so that I could understand what they were doing and ask good questions, essentially. But that I would keep those private, and of course I'll respect that. But I actually think they were very generous to do that at all, and it's actually unusual for companies to say very much about what they're actually doing, to be so candid about what connectors they have and all of these things. Of course, they are at the development kit stage, so they are actually giving their pre-production chips out to companies now, but in terms of the actual detail, how everything works, the exact niceties of the neuron models and things, that's not something that they particularly wanted to talk about, although they did tell me some stuff, which I unfortunately can't share.
But yeah, and now I'm just being the critic, if you will. It would have been useful to understand where they see the immediate impact. Like, for example, are they partnering with folks like Prophecy or some other more established, if you will, neuromorphic sensing companies? It seems like sensing and sensor processing and sensor data manipulation and understanding is very much the core of their application space. So it would have been useful to understand.
Yeah, well, I think about it from their point of view. So they have lots of not just potential clients, but potential collaborators in terms of people who could be providing sensors for them. And you don't want to annoy any of them by promoting their
highlighting one or the other.
Exactly, highlighting the competition rather than highlighting your company. So I respect the fact that unlike us who go out and get grants and things, they have to go and make a living by selling product. And so they don't necessarily want to spill the beans this far in advance.
Yeah, I get it. One other thing I was going to say is the fact that they hit on all the key components, right? So I already spoke about the hardware key performance indexes, but the other part that they hit on, I think that is crucial, is the software interface part and making that stack available. And we've talked about this in multiple podcasts, right? That's usually the valley of death, right? If they can bridge that and make it easier for folks to get their hands on their product and actually use it in some of the applications that we have in our own labs, in our own spaces, that would be super useful.
And just a quick plug for future episodes. So I was just speaking to Katie Schumann earlier this week, and that to her is absolutely the fundamental issue to be resolved in neuromorphic engineering at the moment. That's the most important thing. Giulia, you had something you wanted to say.
Yeah, now I have two things I wanted to say. That there's one thing very cool that Peter said. I just resonated with it, and I want to say it. You shouldn't need a PhD in neuromorphic to do this. And how long people will stop thinking of neuromorphic as something exotic. I totally agree. I asked the first question because the response of what they get from the chip seems very robust and reliable. So I was wondering if I could know a little bit more. Of course, I totally understand their constraints. I have another question, which is a curiosity for the people that would like to try it, but they don't have the ardor in their hands. If there is any simulator, if there's any way to work with APIs to work with these guys.
I think the point is you're supposed to contact them and get their development kit. I mean, I think they are giving away chips and software, or certainly lending chips and software for people who can demonstrate that they have something interesting that they want to do with it. So I think that's the best way to go. My guess is that the chips are going to be reasonably inexpensive because the whole point is that it's ubiquitous computing applications, right? So if they're not fairly cheap, then it's not going to work. So yeah, I would contact Innatera if you want to use these things.
It sounded like they said that they were doing simulations and emulations, Giulia. So, that might be available. Now, whether or not they're prepared to share it, that's another story. I mean, on the simulation environment side, but certainly at least they said they were doing that. One of the things that I want to put a little bit of a plug in as well that they mentioned, and something that you said, Giulia, about the exoticness of neuromorphic engineering, so to speak. I think we've already, jumped that shark, so to speak. So neuromorphic engineering becoming a little bit more mainstream is becoming more and more realistic now. We are seeing workshops that are being sponsored by major funding agencies, specifically in the areas of biomedicine and healthcare, which is, a massive space, right? Sunny and I will be doing a workshop in a few weeks in Baltimore, the neuromorphic principles in biomedicine and healthcare workshop. Might be too late when this episode comes out, but it might be something that you might follow up with a follow-up reading that's going to come up from the workshop, which is about understanding the roadmap of where all the various technologies similar to what Innatera is doing, how it could benefit the healthcare industry and biomedicine.
Yeah, it's a really important application area, I would have thought, for chips just like this one from Innatera, because it's small and it's low power and it can go presumably anywhere. So all of those sensors that you want to hook up to your body, put inside your body, it would be in a good position to supply that sort of micro AI functionality.
So there's one thing that Samit said, where does the industry really require these solutions today? And what is the industry ready for that today? So I'd like to give the same question back at you. Do you see that this application that you're talking about now, today solution, or do you think that there's something else?
No, I think it's certainly not today, as in I'm ready to put it on people like right now, right? But there are certain applications where it's closer, like wearables, everything from your Fitbit to your Oura Ring to your Apple Watch and all that stuff, where it's monitoring one's vital signs and determining whether or not we are on the road to getting the flu or whatever the case may be. So there are other applications where this, on-body neuromorphic computing can be super important. One space that I'm super interested in, and a number of physicians are as well, is continuous blood pressure monitoring, right? Now we see continuous glucose monitoring, but there's no real effective continuous blood pressure monitoring systems. And they believe that's the next holy grail to determine how your health is going, especially if you are at risk of strokes and things of that sort.
I wanted to say something too. When I asked them the question about second guessing what the market requires, what I had in mind is that we're used to products always being a few years out. So you're almost always having to second guess because the market isn't quite there yet. And so you're having to figure out in advance what the market requires. And I think the point about Innatera at this moment, is that they're not looking a few years out. They're looking at a chip that's coming out in a few months and that they're hoping to put into products in a few months, right? Their production chip is coming out very soon. So that gives them an advantage in that they can just say, right now, I want to sell it right now. What do people need right now? And then they can hopefully sell some product, iterate based on the users and what the users say and what the users say that they now need because a year or two goes by. And so they get on that virtuous circle of development with real products in the loop.
One of the things that they talked about was the fact that they have, 340 neurons, something like that.
384, I believe.
Okay, there you go. But it's, as you point out, it's small numbers compared to what we see on various chips, right? However, they made the argument that, well, a lot of the pre-processing and so on and so forth can happen before, it can happen in the RISC-V architecture, and then the application of the neurons themselves may be a little bit less involved in the feature extraction, but maybe more involved in the decision making. And that I see as a potential way forward. Another place that maybe they did not explore, which as an academic I can say these things, and that is the area of where making the chip speak the same language as the nervous system, giving it the connections, the ability to provide inputs to the nervous system that is consistent with what their nervous system expects. Of course, there still has to be a little bit of conversion of the signal of the spikes into the types of electrical signals that will stimulate neurons and so on. So that still has to happen. But there you have a scenario where, you could take the neurons and connect to the spinal cord or connect to the brain or connect to whatever peripheral nervous system that you are dealing with.
I want to ask you about that, Ralph. Is it not true that you would need more power if you wanted to do an application like that? That sort of stimulating neurons as compared to just processing information is actually a harder task in terms of the amount of voltage or current you need to supply?
It all depends where, Sunny. So like some of the work that I've done in the past where we're stimulating in spinal cord, it's nanoamps, right? Or hundreds of nanoamps, right? It's tiny currents, right? If you're stimulating muscles on the other hand, then you need milliamps, right? So it's all a question of where it is that you're stimulating, what is the actual structure. And that changes the amount of, as you say, oomph that you need in order to get it to respond to the stimulation.
But I think one of the things I was trying to say earlier is that there's this strategy of you need to have one successful product or else you can't do anything else. So it's interesting to me just because we're at this moment to see whether it's going to be successful or not.
One place where I disagreed was about the fact that, hey, if you're trying to build an insect brain, majority of the neurons are used in maintaining existence, so to speak, and survival. And, the minority of it are useful neurons and so on. No, that piece doesn't quite fly, right? Where you're talking about the midbrain in the human is 2%. And even in the stomatal neurons, other glias in insects, it's basically a small percentage is actually used for survival. The majority of it is actually used for thinking, so to speak, right? Now I'm putting thinking in quotes, obviously, but we cannot simplify it as they say. So they'll need to, at some point, get a little bit more neurons or synapses or some other computational fabric elements on their chips if they want to interface more easily with the nervous system.
I was just wondering, when you were talking about the biomedical application, what's the latency there? What's the latency that you require and for what?
Again, based on the application space, right? So if you're trying to do something with locomotion, walking, then clearly you need to react quickly, otherwise the patient falls. So that has a certain loop time that is consistent with biological loop times, right? Same with maybe stopping epileptic seizures. If you can detect and stimulate and stop to actually prevent the onset of the seizure. Other places it might not be as critical. For example, another application that been thinking about is what is the mechanism by which you can control, for example, glucose secretion in the bloodstream based on you looking at the food you're about to eat, and then you eat, and then it gets digested, and then the pancreas has to control that, and so on. So if you're going to try to do a control system that tries to help the body to control glucose level in the bloodstream, that may be something that takes minutes, right? And so on. So there, the time constant is different. So it all depends on the actual application, I would say.
But I'd say also it depends on things like, for instance, we talked about stimulation. So just imagine this was the input processor to something that's stimulating your heart. If it's not beating when it's supposed to, then you would want it to be pretty fast. But also, I think the example given in the interview was the feedback reaction with a human. And if you imagine that you've got a physical artifact of some kind that's doing something intelligent and essentially trying to simulate a physical object, if you see what I mean. So it's reacting in some way that's supposed to feel to a human like it's a physical object reacting, then that's going to be a pretty low latency. So I think latency is a big problem in some of these things, and actually potentially even more than if you have a person in the loop, because people are pretty slow. If you have another machine in the loop and the machine is trying to do something fast, like maybe a pole balancing task or some of these kind of control algorithms, well, maybe latency is a big problem there too.
Yeah, self-driving cars. You can't react to that thing. Yeah.
Yeah, in my case, I was just thinking about vision, right? I have the time of a saccade to process things lower than 100 milliseconds. So I was wondering if in this mini domain where you actually need to speak with the spinal cord, if that required crazy, insane low latency. I was trying to understand the differences and if the chips that we have now are already capable of giving you that kind of latency and processing that you need.
So I would say this, the older work from Francesco Tenore, who was in my lab when he did this, where we were actually interfacing with the spinal cord and controlling locomotion, those were essentially direct analog processing of spikes and generating spikes that went directly into the spinal cord, right? So the latency was as quick as the neuron reacted, right? So you detect the signal of the ventral roots, then you assume the dorsal roots, and you stimulate on the ventral roots, and you get the behavior that you want, right? I think that at the end of the day, for locomotion in humans, it might be more a function of, the task at hand, unfortunately, right? I mean, it is pretty much that. We see very short timescales in auditory, for example, for doing sound localization. The differences between the 2 years can be down into the microseconds timescale, even though the neurons are not spiking at microseconds, obviously, right? So if you're going to try to restore somebody's capability of understanding spatial sounds, then maybe you need to do that stimulation with that kind of resolution on both sides of the ears, for example. So I think you'll find that there, maybe you need the super fast time, whereas in other places you might not. So it is going to be driven by the application at hand. One other point I thought that they made that was important is to do with standardization and benchmarking. I think that is going to be important as well, right? I mean, the reason that we can have cross-platform integration, the fusion stuff that you referred to, Sunny, and they spoke of as well. The only way that those works is if there is a standard by which these machines speak to each other and the sensors speak to each other and so on. And I know that in the IEEE, there's been a movement in trying to come up with standards for AI in general, but neuromorphics will be the next component. And we're hoping that this workshop that we'll be doing in a couple of weeks as well, that will have some statements there.
That is very interesting. When the IEEE have standards for these things, then we know that neuromorphic engineering has finally made it.
Thanks, Sunny, for another interesting interview, and Ralph for your great remarks as usual. In our next episode, we'll be talking to Dr. Katie Schumann from the University of Tennessee at Knoxville. We hope you will join us then.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks to our guests from Innatera. EE Times Current is available through all the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find the transcript along with direct links to the other stories we've mentioned and other resources. Thanks for listening.